Okay, welcome everyone to the Thing to Thing Research Group meeting at the IETF 123. First session of the week. Happy to see so many of you over here. I know we had an unfortunate conflict with the dispatch meeting right now, so I know it's a bunch of people who wanted to be here are over there, but still glad to see so many of you made it here. Quick reminder, given this is an IRTF meeting, the note well applies as usual. The short version is that if everything goes well, you are being recorded, be nice to each other, and the IPR guidelines apply. There's a longer version in the following slides, in particular on the reminders about the disclosure of IPR that you might be aware of, on the audio and video recordings, and that you do consent to be recorded if you are in the mic, and also that, pretty much be nice to each other. If there's any questions on that, you can reach out on Ombuds team or the chairs and read the related RFCs and documents. And also a quick reminder of the goals of the IRTF. So at IRTF, we focus on the long-term research issues related to the internet. So we are not a standards organization on this side. We focus on our standards work will be done primarily at the IETF, but then of course we do work very closely with a variety of IETF groups. So whenever we discover things that are worth standardizing, we do that the IETF side. And on the other hand, when many of the IETF groups discover things that are worth more research exploration, it's commonly done over here. Quick note on the admin side. So we do have notes online at the usual location. I will be taking notes. Marco kindly volunteered to also take notes, but also anyone feel free to chip in if you missed something perhaps you said or misinterpreted. You can edit the notes doc online. If you are not already on the Think Research Group mailing list, please do subscribe. There you get notifications of the related activities and all the meetings, etc. So highly recommend to follow that. And as usual, we have a GitHub repository for the meeting where you have the latest agenda and some of the more logistic informations. Quick note on the document status. We have currently 2 documents are getting ready for research group last call. The taxonomy of operational security considerations for manufacturing installed keys and trust anchors. Both of us chairs have reviewed that, so only minor comments. So I guess after final update of the draft, I think it's going to be ready for last call. So we expect to start that shortly. Also, there's the kind of RESTful design for IoT that is pending. One more review run on the chairs, and then we believe we will be able to also last call that. So now is also a good opportunity if you haven't read those drafts recently, give them a look and send your comments on the mailing list. There are 2 more drafts that are work in progress at the research group: amplification attacks using co-op and terminology and process for initial security setup of IoT devices. Both of them are pending updates, especially application attacks. We believe only small updates before last call. The terminology part requires still a bit more work. And then there are also individual submissions that are not currently work group documents using, research group documents upcoming for adoption. So using onion routing with co-op and this distribution software updates with end-to-end secure group communication, block-wide transfer co-op. The second one is also on agenda today. So they are also interesting documents that seem to be something that we could be potentially adopting in the research group. And then the agenda for today. We're right now in internal logistics, almost done there. Next, Carolina will be giving us a speech on why are smart buildings still dumb. She gave already a teaser on the topic earlier on an interim meeting, which seems very interesting and relevant for the group. So we wanted to have a bit longer slot here to go a bit more into details and on a wider audience. Followed that, Greg will be talking about IETF, IoT frameworks and standards for secure communication at the energy edge. So around the utilities areas, what are the interesting requirements they have and what could be the IETF systems be able to provide there. Followed that, Jaime will be talking about agentic AI operations of IoT systems. So AI agents, obviously a very hot topic. And of course, there's a lot of interesting things that the IoT systems and protocols could be doing there. So Jaime will give a glimpse of that and also a demo that we hope will be working out on live. And finally, Marco will talk about the software updates with group communications. Also something that we had discussed earlier in the meeting in shorter form, but now we'll go in a bit more details and more refined. And then finally, we hope to have a bit of time wrapping up everything, drawing some conclusions and way forward. Any questions or comments on the agenda? If no, then Carolina, please.
Yep. Okay. Hello. Do I need to turn this thing on? Hello.
Yes.
Yeah. Okay. Great. So after that little awkward microphone thing, I hear many people have been dispatched to the dispatch meeting, so there is a bit less pressure for me. And so today I would like to talk to you about smart buildings. So I'm sure probably many of you have their own home automation, or at least maybe you've struggled with an AC in your office building. But the thing is, well, the smart buildings or the idea we got from IBM brochures, it seems they haven't really lived up to their potential in reality. So today I'm going to talk to you about our research agenda of how to brew the key characteristics we believe we need to get buildings which are truly smart. So evolvability, security, and resilience. So what is it that what we think about when we talk about the smart building of the future? So it could be something like we want frequent layout changes with integrated robotics in the environment. So like we change the workspace to an open cooperative space, or we have custom HVAC zones. We have low maintenance costs, or we have better energy efficiency, or it's like the real, truly good advanced stuff, such as the lights don't turn off when I've been sitting at a desk for 10 minutes without moving, or speaking from a real scenario from an unnamed university, we are actually able to integrate CO2 sensors during a pandemic, unlike after 5 years. From hundreds of deployed CO2 sensors, there's 20 which are actually integrated into the university BMS. So there are two general approaches in industry to building automation. So on the one hand, we have the industrial automation approach, where we have like very expensive controllers, which are running the control architecture in a more decentralized manner. They're quite reliable, which is nice, but they're extremely expensive. So which creates ecosystems which are very rigid. There's lots of vendor lock-in. It's very difficult to adapt them to current operator or user needs. So what we're actually running on them are fairly rudimentary PID loops and rudimentary control policies. It's hard to do anything fancy. Then on the other hand, we have like the more home automation approach, where we have a bunch of smart devices running the control architecture on usually some kind of centralized box, which is sometimes in the cloud, sometimes not, if it's something like Home Assistant. It's much more dynamic, which is nice, but it's also very high maintenance and very unreliable. So again, we're getting essentially like fairly rudimentary control policies. So the general pattern seems to be that as we have more devices in our system, we are getting lower dependability, the maintenance costs get higher and higher, so the trade-off isn't really worth it unless you have a lot of money. But we don't want to use the systems in like fancy Google offices. We would like to use these in schools and hospitals to actually improve energy efficiency and user experience. So could we have the best of both worlds? Could we have lower cost automation systems which are actually reliable? So we figured, could we take the home automation lower cost approach and make it reliable? So what we want is to run a complex control policy for decades on like the home IoT style building automation system. So what do we have? We have a bunch of devices that are quite flaky, so they suddenly just like disappear from the network for some reason. We have the central box, which is like more reliable, which is why we like to outsource most of the control compute on there. But the links we usually have to transit to get to it are also flaky. So overall, not too great. This approach is quite easy to deploy. but it's not resilient, it's not secure, and it's not evolvable. So maybe we could do something more like the industrial control does, where we actually deploy the control architecture on the edge. So we're taking the server out of the critical control loop, not entirely out of the question. We still need it for configuration, authorization, all the good stuff. But we just deploy all the control on the edge devices. So we transit the link a bit less, maybe. So it could be an approach that could work. So let's just take like a simple example of a control system. So we have some motion sensors and we're reading values from them, making like processing it in some way to decide whether we want to turn the lights on or off. So the system, if we want to adapt it incrementally over like the long period of time in deployment, it's to involve on the device and the system, so network of devices level. So first of all, what do we get from a single device? We need to know that because we're going to lose a lot of the devices a lot of the time. And we know that, so we have control system, which means there's a lot of explicit and implicit dependencies, meaning the failures can have a cascading effect. So first thing that is really important for our control architecture is the control compute that the device does, not necessarily the specific network stack we're running or other utility functions. We care about the specific control tasks that we lose when the device dies. And second of all, the same data sources and things it provides to other devices or gets from other devices to be able to execute control. So what we would like to do with this device in order to actually evolve and adapt is, first of all, take old software that we're running on some previous device and just stick it on a new device, which sometime later is going to come from an entirely different vendor. It might be have many sources of incompatibility, but in order to easily integrate it, we would like to run the same control application on it. And then, second of all, we would like to run new software on an old device because we want to improve what our software does, or we want to change what does. For example, instead of taking an average of readings, we want to take median to because of outliers. So now we run into our first issue because I suppose if any one of you has ever bought a smart device, they usually run locked down firmware from vendors, and they don't really let you change what you run on the device. So, oops. Yeah, you could argue that, sure. Uh, so, kind of the situation we have in here that over time, with like new hardware product, we always get new software on it, and maybe sometimes if you're very lucky, from here and there you get an update. So we can't really specialize like it doesn't make sense to invest a lot of money and effort into developing that software, making it better, more advanced, and we also can't distribute responsibilities to different vendors who would take care of our large control system. So if we want a system that can actually evolve and become better, we need to free the software from from the hardware. Um, if we want any semblance of evolvability and security, because we really want updates, right? So instead of something that looks like this, we want like an independently evolving software lifecycle. More than that, we need different components of the software to evolve independently, especially the control that we want to run on it, to support something like an ecosystem that actually supports evolvability. So, okay, let's assume that we can do these things with our device and consider like what do we need it to do to actually perform useful work as part of the network of devices. So there are, I would say, are like four main operations that we need to support. So first of all, we want to add new functionality as we add new devices. So for example, in this case, we have like a new, more capable device C that has a really great also motion sensor, and it would really improve our accuracy and to, for example, not turn off the light because we're sitting at the desk because it takes it into consideration. Then, if that very wonderful device dies, we would like to go back to being able to do what we did before, still being able to turn the lights on and off with our motion sensors because we still have enough of them.
Carolina, is there now a good place for a question? I see Hannes on the queue.
Oh, yeah, sorry.
I, yeah, I had to, or I felt that I should comment on your earlier idea that that we should end users of products should be able to just update the software and or write new software, add features and so on. And I think that's a nice idea in conceptually, but I believe it misses the point that these devices are purpose-built devices. And that really means something. It's not a general purpose laptop or some other computer where you can buy it in the shop and then use it, but they are really built for one purpose only, and they are locked down because of security reasons, like secure boot and all of that, so that you shouldn't be like what makes you as an end user different from an attacker. I'm using yep. Oh. Oh, okay. Yeah. So this is so loud, even in Austria they can hear me. I can actually really stand back. And so you write some software, load it to the device, and how do you prevent other people from making these changes? And I think that idea of taking someone else's device and then change the code and do whatever you want with it because you're unhappy with the speed of development there, I think is will be even more difficult in the future as we are now entering this Cyber Resiliency Act, where lots of responsibilities are delegated to manufacturers of those devices, and they will delegate it on. So I think this will be very tricky to do. And I'm curious on how you envision this to work, because this is not just a technical issue. This is a business model issue. This is a regulatory issue, and so on. So I'm curious on whether you have some thoughts on how this is going to pan out.
Yes, so amazing point because I will address that a bit later on. Yes, so yes, exactly. So like if you're trying to change the software on device, you're gonna get more security issues. So there are some design aspects we're trying to introduce to start addressing that, but also starting with that. So the devices which are already in production are not actually secure. The systems aren't secure. So yeah. Well, I don't know, like talking to all the people in our research IoT security labs, like that there's so many vulnerabilities on devices and data leaks. It's just also.
Okay. Okay. Maybe it makes sense we take a quick clarifications in between, and we could take a more detailed discussion in the end.
Yeah, we can
once
also discuss
Caroline has a
afterwards.
chance to cover. But if you have some quick clarification, go ahead.
I just wanted to understand when you mean changing the software. As he's just said, those devices are purposely built. I see a huge difference in changing the software versus allowing users to configure policies based on things that the device is purposely built to do. So user-defined policies on a device is not like changing software. It's more like just configuring something on a user preference level.
Yeah, so I will talk a bit more about this as well, but so what we're mainly talking about is trying to take advantage of the extra processing capability. So because the smart devices are running like hardware which is actually fairly capable already. So we don't, if possible, it's like we don't only want to use it to collect some sensor data and send it on. Maybe we could actually make it something more useful as part of the integrated control architecture. Also, I'm not here talking just about like an end user setting up like their own home automation, but also talking about like more serious deployments in something like an office building where it's very different, like where it's um, the hardware of like industrial automation is so expensive that it greatly limits on what the like people operating the system can do. So having like a I guess a more like some guardrails on where you can like hook parts of the control architecture onto the device. Yeah, not necessarily like being able to like willy-nilly reflash the whole firmware on the device. Yeah, if that makes a bit more sense.
Uh, yeah, I think when we say it's expensive, it's cheap, I think we have to keep in mind that there's the hardware, the real hardware cost, and then there's the cost that comes from the whole manufacturing and from many other, there's cost that is related to many other tasks that are unrelated of the software, so or unrelated of the hardware that we think, oh, we look up the, what is the cost of the bill of material, and it looks like very little compared to like what the box ultimately costs. But then there's all these processes around it, like certification. You need to, like, there are lots of people who work on it. There's, for industrial devices, there may be even like special design software running. Like you need to rip out everything. You can't just use off the shelf stuff because you have all these requirements on real-time guarantees, which you don't get from just downloading Linux and then running it. It's a completely different universe. Like I know that some companies have spent like 10 and so on years on working on some of those things in an army of people, and that costs a lot of money. Plus, you need to have the support for 20 years, and that costs, and you need to factor that in. This is something that we as engineers often don't see, but the business people need to make that calculation. And so what looks like, oh, I could do this in my lab for like $100 is in reality like way more expensive. So we need to be careful on our judgment here.
Absolutely. So I'll like a really big chunk of the cost for industrial devices, like for deployment, is actually the installation cost. So the hardware is very expensive, but actually installing it is like the biggest chunk of that. And then so when talking about industrial control, yes, there are real-time requirements, but it depends on the specific application. So when when we're talking manufacturing, there are some like very hard real-time guarantees that you need. If you're talking about building automation, then the usual deadlines we're talking about are like in the hundreds of milliseconds. Like the most sensitive part of the systems is something like an air pressure valve, and even that's in like scale of like tens of milliseconds. So part of what we're trying to use in here is like the extra leniency we have in that, and like trying to build and kind of like an extra abstraction to ease the deployment of the control architecture, if that makes sense. But yeah, we can absolutely discuss that into like depth, and I think yeah, that's absolutely a very good point. And part of what we are trying to address is how the business ecosystem could work a bit better. So yeah. So going back to the things we would like to do with our network of devices. So yeah, we want to be adding functionality, like retaining functionality when the devices are lost. Then of course, at some point we just like lose enough sensors and like have enabling failures where we can't actually like get the like, sensing capability that we need to make a decision. But maybe we could fall back on something that's a bit worse from our system. So for example, we can't decide whether someone's in the room based on the motion sensors, but maybe we can look at the trends of the CO2 levels or something, which is not as optimal, but like it's something, and we can figure out whether there's someone in the building and turn the lights off if there isn't. And then lastly, of course, extend functionality with our existing set of devices. So for example, if you want to add a new feature that can only be implemented in software. Okay, so when we're looking at this at these operations, like what we're kind of doing is changes to like the control task graph. So like the abstract kind of the implementation of the control architecture. So like where the nodes are the kind of simple like pieces of compute and data flows between them. And then we're essentially taking this graph and we're mapping them onto the devices to deploy them. So some of these tasks, we clearly know where they need to go because they have hardware dependencies. If we're reading from a sensor, we need to be on the device with a sensor. But for other tasks, this is a bit more unclear. So for example, some more general processing like averaging or making decisions can be deployed in many like on many devices in our network. And we may make the decision different depending on current conditions. So for what is the current link quality, what is the processing capability of these devices, and those conditions are going to change over time. So if we want to avoid our system to continuously degrade in functionality, we really do want to adapt the mapping of the control task graph onto our set of hardware devices and the links between them. So for example, when we consider like the original example, if you're adding a new device C, we're essentially adding a new node into the control task graph and deploying its data flow over a link between C and A. And then actually, because this device is much better, maybe we could outsource more compute onto it. So for example, change the mapping of the average task from device A to device C. And then when the device dies, well, we can just go, we can get a new copy of the average container and restore functionality. How do we actually try to do that? So let's just go over like the idea of our approach and then go to some implementation details. So we are making the control tasks in the system explicit and drawing them out from the binary image. We deploying them on the devices which run currently our platform called Chaos, which actually manages the containers and which handles access to external resources. We establish communication channels between them for the data flows, and we consider a set of like orchestrator entities to handle the authorization, configuration, etc., and the changes to the current mapping. So you would say that that is quite a lot of things for a smart device, like in your usual like home deployment to do, or like for considering what's available on the market. But when we take an ESP, something like ESP32, which is already very widely used in like smart device products, it is actually very capable, and it can do something like this. So first, let's take our portable control tasks. So they're helping us to actually do the hardware-software decoupling, because we can divide the software on the device into a set of containers to distribute responsibility for different parts of the system to different stakeholders and run it on various vendor platform hardware. So this might now make more sense to actually invest into the software we develop and changing devices a little, so giving us some of our evolvability characteristics. And it also allows us to restart computation and move it around to adapt the system, helping us to deal with failures. So what are our containers? So in this case, we're actually using WebAssembly, which you may know for like computation in the browser, but it can actually be deployed on ESP32. Of course, this is still on has a higher footprint than some available container runtimes like femto containers, if you'd like. That's also an option. We're not being dependent on a specific runtime. This is just what we use because of fairly good production support. And one of the nice things it gives us is isolation. So that's starting to help us on our way towards security. It's not, of course, all we need, but it's something of a good start, because as the point was raised, we are dynamically loading code on IoT devices, which are already fairly insecure. So we're kind of making the situation worse before trying to make it better. What WebAssembly doesn't really help us with is the system call interface. There is no well-defined interface, especially not for control application use cases. So of course, our containers need access to external resources. We need to access hardware peripherals, and we need to talk to other containers. So what what we use for this is like we establish communication channels between the containers using message channels, which gives us kind of like a restricted API of put and get. So because we're looking for something that's very simple and future proof, because while the device, the platform that's running on the device may change, the runtime may change, but what's in between, that is the important part. So it needs to hold up to time. So the communication channels, it's there partially to also limit direct network access, because we want to limit what kind of damage a malicious container could do. We don't want, especially in a control system where, again, we have the potential cascading failures. So instead, we decide to expose a set of communication services. Now, again, what we're being helped by is that we're looking at a fairly specific application, like building automation. So we have certain types of data we want to transmit, and we have some leniency in terms of real-time characteristics, which also helps us. So because the communication channels are managed by the platform and they're not inside the container, if a message has arrived and hasn't been gotten by a container for processing, if the application suddenly dies, the data is still there. So it helps us to actually restore service when with application failures, and to deal with some adverse events. So how does this allow to do things like dynamic component placement? So actually adapting the deployment of our control architecture. So let's just go through like short life cycle example of a system. So first, like we're loading some configuration of our control architecture from an orchestrator and set up communication channels between them. And we're running our applications. But then actually we want to add in a new device into our system because it's better. We want to improve our sensing capabilities. So we're just plumbing in to add a new data flow to the average control container. Then again, because we want to improve the performance of our system and this device is more capable, we actually remap the average container to this new device. And again, we're happily running along. But oh no, we were lied to. This device is actually not reliable at all, and it fails on us. But we can start a new copy of the average component, the one that we really need to restore the service because it's not otherwise running anywhere on the system. And again, restore our application. So being able to dynamically adapt to current system conditions by dynamically deploying our control architecture, we can tolerate unreliable hardware and links and deal with adverse events in the system, giving us some semblance of something coming towards resilience and evolvability. So what we think is to get secure and resilient IoT hardware is to have like small chunks of compute representing the control architecture and have the ability to deploy them on our system dynamically. So now points to think about, because of course devil is always in the details, and I didn't have enough time to include many details in the presentation. So first of all, interfaces. We talk about things like managed communication and what services we expose. And I'm sure that like many people have many different opinions on what those should be, and it should be part of an active discussion. Then again, we're essentially creating something like a control abstraction layer, and we need to decide on like what should that exactly look like. Then things like if you're dividing the control architecture into chunks of compute explicitly, what should the granularity be? There are different trade-offs to that. And how do we support the integration of such a system into legacy systems which do not support running custom changing parts of software on the device? Then, of course, the big high-level issues like what are the specific mitigation strategies we would like to deal with failure? How can we better implement updates on the system? So, like doing things like rolling updates, etc. So, kind of concepts we already know from other digital systems that, but we haven't really been able to properly implement in automation systems, or what development tools we would need to properly debug these systems. So that's all for me for now. And thank you, and please ask questions.
Great, thank you, Carolina. So now we have a bit of time for more detailed questions. Or if you want to follow up now, Hannes, or no need to go now. Well, maybe one question I was wondering about the so this is like a lot of conceptual what you describe here, and how much has been realized so far, and kind of what have you thought about the actual realization technologies, like and coming kind of from IETF, IETF angle, especially on the protocols, data models, security mechanisms, etc. What's your status and thoughts around that?
Yeah, so we do have a working implementation of like the device platform. So we can take apart some control tasks, deploy them on devices, and manage them, move them around. We need to implement authorization for containers because, of course, so the idea is that when a container arrives on device to be deployed, it comes with a manifest from a certified authority that includes things like what other containers is the container allowed to talk to, uh, what um, what API is it allowed to access from the device. So if we're talking about accessing some hardware peripherals on the device, those are exposed as an API available to the containers locally on the device. So all of that is specified to try to constrain what the container itself can do. And then, so we don't have a full working implementation of that, but that's the idea in terms of security. And then we have a lot of ideas regarding orchestration that haven't been implemented yet. But we want to we have so far tested things on hardware, so have like a small test bed of several devices. But we would like to, like, I'm currently working on building an emulator to have a deployment of like hundreds, thousands of devices to test things out.
Okay, thanks. Looking forward to hear more. Now I see Hannes on the line. Go ahead.
Oops. Yeah. I was wondering about the following aspect. If you switch to a more, so you're already looking into more powerful devices anyway, and if you switch to sort of like a more capable device that is able to run embedded Linux, you could essentially deploy this like you don't need to do any implementation work essentially. All of this exists because you can do container orchestration, you can apply whatever your favorite technology is of the day, and be done with that. And you don't need to rely on WebAssembly either, because that's also a hassle. It was very popular at some point in time, but then faded out of sort of like, it looked promising, but then it wasn't. So I'm trying to.
It still seems promising.
It to you. For example, if you would just use Docker containers and deploy this, I think that could be extremely promising. You could get very cheap hardware and deploy it on those edge devices. Give you also a little bit of headroom. It also has the capability to provide various different, or benefit from various different developments in the security area on like the certificate management and some of the other groups that are working on this. So you would get that. And I was wondering why you haven't taken that extra step, because I think you are tackling now with problems that basically come from the choice of better hardware, but not quite there. So why did you go that path?
Yes, I guess that's the question of how better do you think the very cheap devices will get? Because so when we think about an ESP32, you can get like a board in bulk for like maybe 40p, something like that. like when you're talking about something that like runs Linux and can support Docker, that is going to be more expensive. So I think there's a point to that, like how good the hardware will get that we deploy things on. But even if we're talking Docker, how do we want to constrain the interface and like access to external resources for the containers? Because that would still be an issue, right? But
But that is an issue that's being solved in like the broader industry scale. And
is it?
yeah, well, you can still argue whether Docker is good enough or you should go to virtual machines. Um, but the one additional sort of industry effect is like everyone talks about AI. They want to do edge AI. And so that's like, if you look at the most recent hardware sort of announcement of different vendors, they all have sort of massive new capabilities in terms of compute power and also more RAM because the machine learning model need more RAM. You have more flash because you need to store them somewhere. And so you get that, you already have that trend as well. So I see a spike in performance from these constraint devices for some reason because they now want to jump on the AI bandwagon. And if you take also that into account, you are very quickly there where you are with a Raspberry Pi, old version of a Raspberry Pi. So yeah, maybe requires some digging into the numbers, but the boundary may be really fuzzy. Of course, the ESP32 also has the radio interface, which like a general purpose chip doesn't have. But you also need the security platform as well, which ESP32 isn't particularly great at.
Yeah, exactly. I think that it's the like trying to see how the numbers exactly work out, also to get the kind of the cost maintenance benefit that we want. So yeah.
Yeah, Carsten Bormann, I think I fully support what Hannes said, except that I don't accept the consequences. Um, so, Dockerization, containerization. Imagine that at a time in the past when we found out that maybe it's a good idea to have some client functionality with a web application. Imagine we had decided we're going to do this with virtual machines. So every browser becomes a virtual machine hypervisor. And in order to use a web page, you just first download the operating that runs that web page operating system and run it on this virtual machine environment. That certainly would have been possible, but for some reason, people did something different, probably because at the time virtual machines weren't quite as far along. In computer science, we rarely solve new problems. We very often solve old problems for new environments. And I think the main point that I really want to underscore here is we have to be sensitive to the kind of environment that we will have in 5 years, in 10 years, and so on. And that's, of course, very hard to predict. I think the one important consideration that we have to keep in mind is that we want to have many of these devices. And if we have many of them, not each of them can consume a watch. So we have to think about how do we do useful functionality on a platform that is very frugal with energy usage. That's where we want to go. And that's why Raspberry Pi kind of, yeah, you can do that, but you don't want to live in a home with 40 Raspberry Pis because you will have to upgrade your air conditioning. Again, old problem, all old solutions qualify, but maybe our parameters, our environment is a little bit different, and it's worth thinking about new approaches, even though this is a solved problem.
Hi, Manny Fontaine. I wanted to echo what Hannes said and what Carsten said on the security piece and the 5 to 10 year horizon. I think over the next couple of years, you're going to start seeing more and more low-cost silicon that's going to come out with trusted execution environments, confidential computing type technology, hardware cryptography, and things like that. And that fundamentally changes the way you handle device identity, authentication, authorization, key management, decentralized computing, and things like that. Smart devices are smart not just because they do things within your environment, but also because they connect to other things beyond your authority, right? They connect to systems that connect to other systems that are under the authority of other entities. So we really need to think about these problems, which I very, very much empathize with. I'm a hardware engineer by training, but we need to think about system design at global scale. And trusted execution environments are major, major steps that are going to become mainstream in the next 2 to 3 years.
Yeah, you're right, especially so that's something I think just supports the ability, the want or the to support like more dynamic ecosystem, but to actually dynamically load code on devices, because we do have better embedded devices with better security capabilities, like with supporting encryption in hardware, etc. So
in response to Carsten, so I think the shift from sort of these higher end constraint devices to low end high end devices is probably faster than we think. Although I don't have numbers, and probably that would be a good exercise to get some numbers there. But there, I don't see, if you want on one hand that flexibility that you described in your presentation, with like I write software, or everyone can write software and then deploy services and so on, that will sort of favor a model that is more like an embedded Linux style, because there you can obviously have a lot of options. And I'm not sure whether this sort of the earlier Raspberry Pis would be such a huge hit on the energy efficiency compared to some of these modern ESP32 type of devices, specifically if you use them with container WebAssembly orchestration type of use cases. So I guess we need to look into the numbers a little bit to see whether that really makes such a big difference at the end of the day. But it will make a big difference from a developer point of view, and also from a security point of view, because still getting the development of, let's say, Cortex-M microcontroller programming right is really hard still today compared to embedded Linux programming. Like everyone can do that. And the last point I wanted to make is, which I now forgot, the WebAssembly aspect. I was very enthusiastic about WebAssembly a few years back, and I had my coworkers working on confidential computing, which we just had with Manu. In there, it was unclear what the favorite technology for compartmentalization would be. And it turned out, and WebAssembly was one promising candidate where people looked into. But then, again, it's an abstraction that is nice, but then it's still cumbersome, because it's not the sandboxing, like the Java virtual machine sandboxing, that is the issue. The problem is coming up with all the interfaces that reach out of that sandbox, which you need for these IoT devices to actually do something useful. And so you need to have so many of those APIs, because you not just need the APIs for the sensor access, but you also need them for reaching into your security. You need to have some persistent storage, etc., etc. So there's actually, then it looks more like a cheese rather than like what you think, like nicely segmented code.
Exactly, that's what we're thinking of instead. To provide, first of all, so for communication with other containers, we want to have some predefined set of services to support, and then in order to access hardware peripherals, just expose, like the device would expose a custom API of the set of functions that it allows the device to access. So and the device can access all of that API, just something that it is in its manifesto, so what it has been authorized to access. So maybe it's some of that kind of approach to avoid the cheese issue. Again, like you do have to think a lot about the interfaces. That's, I think, one of the that's one of the main points.
It's sort of like everything looks great. Like you remember the days MicroPython? We also thought that would take over the world, but then also it didn't, because it's
It's very funny, because first we were like running stuff on MicroPython actually.
So I'm getting out of the implementation discussion on the technologies. I wanted to come back to a little bit some of the architecture points that you were pushing. On one of your first slides, you were explaining that, and I understand the willingness to go that way because it's always been also of interest for me in the industry, a full mesh capable system where devices can talk one to each other directly without, by removing a central controller, which you were mentioning as a point of failure. But I mean, there are ways to avoid point of failures even if there's central controllers. They can be redundant, there can be, it adds cost, but when you're talking about industry level or smart buildings, I think that level of cost doesn't really come into consideration as much as I'd say consumers. It's a different point. But when I was coming back to the orchestration point at the end, even if the devices can talk one to each other and so on, you're still going to need, I would say, a central orchestration point for the management people to define all of the policies of everything working together. And then it's going to be pushed to all of those devices. And if something fails, you still need, I mean, the failovers are not necessarily going to be completely automatic because, as you said, you may want to come back to a previous configuration, but that will be something someone will have to find. I mean, making this fully autonomous is, I don't think so. You're still going to have that central controller either for flows, for communication between devices, or you get out of that communication and you only use it for orchestration and provisioning. And if you remove the central point for traffic, you create a lot of security concerns because if all the devices can talk to each other, you have a lot more breaches possible in your network as well.
Yeah, exactly. That's why, again, we're trying to have like very restricted set of communication channels that are authorized. So you limit who the devices talk to. You do have, yeah. So you're taking this central box out of the critical control loop. So from the direct control communication between devices. And yes, you still need it to make the orchestration decisions, but also because there are some things that the device can do. Maybe it can keep a copy of a container to actually, if to spin it back up. It's easier to spin up redundant containers. Like you can make more decisions and you can start thinking about the mitigation strategies, like which you weren't able to do, like which you're not able to do currently, because the ecosystem is a lot more rigid. If that answers your question. I'm also happy to take it further offline.
Okay, we leaving our allocated time for the slot. Craig, since you are next anyway, you can make your point from this end of the room.
Fine. This is funny.
Great, thanks a lot, Carolina.
So my question was, are you thinking about, well, the orchestration you're talking about is critical and largely technical in keeping things running. There's another sort of policy orientation that I've seen in building management, which has to do with buildings, as they say, getting out of tune. So if there are any user adjustable controls or parameters in a policy, there's another level of setting boundaries. It can never use more than this much energy. It must never go beyond these environmental constraints. So are you thinking about that?
That is like exactly what we'd like to try to enable. So you basically have like a multi-agent optimization environment. And that's exactly like what we're trying to like think of as like the end goal. Also, there was a point about like the cost in industrial buildings. So just wanted to comment on that because I forgot. So I have talked to a lot of people like who are operating building systems, whether on like university campus or like people in industry. And it is very much both costing and the cost of mainly cost or actually sending out someone to replace a node or like to install something that is wired is so high that they don't do it. They just don't have the finances because it's extremely expensive on the scale that we're talking. So even like set of 20 buildings, that seems to be a consideration so far. So, yeah.
Thanks.
Okay, thank you, Carolina. So we are now going to maybe another end of the spectrum where we want to have way more reliability, way more control, and so on. But I think for this group, it's really important to understand this as a spectrum on which there are many places. So even if we maybe care more about smart homes, I think we are very well off understanding the environment that Greg will be talking about. You have a clicker.
Thank you. Yeah.
Left and right.
Thank you. Yeah, so thank you very much for the opportunity to share some thoughts with you today. I work in a place where we have power labs running what we call low voltage, meaning up to 15 kilovolts, down to service voltages that you use in the wall. But we have power emulation, power simulation, a lot of hardware in the loop and things like that. So I'm coming from a place working elbow to elbow with power engineers who are trying to figure out how particularly towards the energy edge, as we say, meaning buildings, environments, campuses, environments where users will have more involvement in deploying energy generation and managing energy consumption with microgrids, with distributed energy resources, photovoltaic and wind and battery storage and things like that. So what I'd like to do is give a little more context of a problem that I'm working on. I'd like to say how we're jumping into an environment which is not really that receptive to IETF, IoT, constrained devices kind of thinking, or anything having to do with the internet, but I'll say more about that. I'll describe the use case of self-healing adaptive resilient power systems. It's a project that we're pursuing, and I'll describe the goals there, and we can have some discussion. So, like in many other industrial environments, the engineers working on power systems just basically distrust communication. But they have good reason, and their natural focus is on safety. And I'll be talking a lot today about what we call circuit protection, meaning making sure that nothing is going to ground and causing fires or disruptions like that. And they have what I call deep cultural commitments. Let me describe what I mean. If you're running a utility distribution system, so everything from the bulk power system that steps it down from, I think in Europe, typically an RTO, a regional transport operator. So your utility, for the most part in Europe, now takes that and makes sure it gets to your home safely. And it goes up and down the feeders and the buried wires and everything that accordingly. They will spend labor energy. They will have old-fashioned analog methods. And if they work and they're sustainable economically, they will not change them. It's that simple, right? That's what I mean about deep cultural commitments. I'm sure you see this in other industries as well. We've heard about safety constraints, timing constraints, cybersecurity constraints, and all of them have their reasons to be skeptical. But I love IETF IoT, and I'm going to make them think about it. So their objections are the comms are slow, they're unreliable, they're vulnerable to interruption and other things, they're expensive and exotic. They have a good point, because where they do know about communications is in that bulk power system I talked about. They have optical fibers everywhere, and they have very expensive communications equipment, switches, and not even routers. It's basically a switch network on the end of those, and they can do amazing things like drawing huge amounts of data, do modeling. They have these things called phase measurement units, which can talk about the the voltage, current, and phase of what's happening in all different points of a wide area, and they're very expensive devices. So in the distribution plant, where they have many, many, many more miles of wires, where they have many, many more end users, not just distribution nodes up to the transmission, they have to think about the economy and the practicality of that. In particular, generally when you put something in the air or in the ground on a pole, or you never touch it again for 30 years. So that's one of their mentalities. So these are the deep cultural commitments I talk about. To ensure safety, there are these things called protection schemes, and relays are now largely digital devices. They're a small, but not tiny computer on a 19-inch rack or perhaps up on a pole. And they can do calculations and then turn a relay, as you learned in high school electronics, whether on or off, right? So segments of the wire will be empowered or disempowered based on short circuits or running out of bounds. And that's what we mean by protection, okay? So the end devices are self-contained and self-reliant from a communications point of view. They don't talk to anybody. What do? They measure local values of voltage, current, frequency, and phase. And then those values are used in an algorithm that runs locally, which has been designed to work with everybody else within a state space. No communications necessary. How do you make sure this works out on a large scale with dozens or hundreds of these relays? Well, you run simulations using these algorithms in the simulation. You adjust boundary conditions and push them different ways, and the system rolls out without any communication. They do change the algorithms occasionally, but not over the air. And if they do, the vendor has to come and make sure that happens everywhere. And as I said, then you'll have a line distribution engineer or technician climb the pole and do a firmware update. That's the world we're looking at. So the problem statement from my point of view in terms of being able to do some research is this deep skepticism doesn't pan out when you have more and more devices and systems at the edge of the grid. You have photovoltaic arrays, you have energy storage, even in your home. And we want people to be more and more able to choose what they use as energy and to be able to purchase inexpensive energy systems and devolve from, I want them to be able to devolve from this big, massive machine, but work well with it, okay? So the situation I'm describing is only complicated by natural and very economically and environmentally favorable developments that are happening. So what are we going to do? When I talk about a strategic intervention, it's like a psychotherapy term. And I'm joking, but these people are stuck in their culture. They can't change. They want to change. They know about really cool things like grid forming inverters and new technologies that are coming in. But because of the resistance, I've had to find a place where a colleague of mine is open to what we call introducing just enough communications. So something that would be very helpful and beneficial and improve what can be done. In fact, do some things, enable some things to be done that cannot be done with the traditional methods, which I'll describe, but is not mission critical. If it failed, it could still get most of what they need to get done. So let's look at that. We need to satisfy the requirements, which are stringent. It has to be very low cost. And by that they mean no more than about $1,000 all in for adding a node into the network, a communications node into this distribution system. The performance is really relaxed. It's much less than one coapp payload worth of data coming out of these things whenever. It's not even time critical. Packets can be dropped, it can be repeated. It has to have coverage through their area. It has to be able to pretty reliably, at least with retries, get to other nodes, and it can be a mesh or it can be hubbed or whatever. That's all fine. It has to be secure, of course, if they're going to touch something as exotic as communications. They need to be assured that over its life cycle, it's not going to become a vulnerability. I hope you're in your mind thinking about, oh, we have stuff for that. Oh, we have solutions for that right here in IETF. As I say, sufficiently reliable. And by that, physically, it has to be highly reliable for reasons I've mentioned. But in terms of communications, it's got to be a best effort. And we've already seen this kind of thing in an adjacent area for automatic smart metering, which I'll talk a little bit about. and it has to be scalable, and that has to do with the price and particularly in the installation. It has to be easy to put one of these things in, and it should auto config so that nobody has to worry about it. If possible, build on open standards. I'm pushing this very, very strongly. I'm saying it's the only way to go, because we'll have to engage the vendors after we've shown how cool this stuff is. Some thoughts on that later. And then demonstrate viability first through co-simulation, but we can also do lab prototypes. We have some systems where we can go over miles of feeders and with a cooperative utility and try this stuff out, even including photovoltaic and wind energy and storage that we have in our plants, in our lab. So my strategic goals are just to find a way to prove to the power systems community that there are practical and scalable communications-based control systems that can be deployed. This will then open up a bridge to systems not under the utilities. I believe this should lead to communication with systems that are sold by somebody else, not in the utility supply chain, but that can then join a community of energy consumption and generation and consumption that's multi-party. And of course, that's where standards-based and auto-conf or low-touch configuration, things that we know about, come into play. And then, of course, build on the frameworks we know. So the system is called SHARPS, the Self-Healing Adaptive Resilient Power Systems. And the goal of the project, which is running for 3 years, and we're in year 1.5, is to create techniques and algorithms and eventually devices that enable distribution level power systems to self-heal. What does this mean? It's pretty well defined. When a severe event, a weather event, usually weather related, but would normally lead to a widespread outage, that means dozens and hundreds of homes, maybe thousands of homes without power for a certain amount of time, the power system is able automatically to re-energize all the loads, that's your home, for which there is sufficient source capacity. In other words, there are generators available to actually supply the energy you need. Don't want to connect them if you can't power them. And there's a path from here to there that is safe. So you have to have a sense of connectivity for the whole power system. Secondly, maintain voltage and frequency regulation. Of course, you have to deliver it at 50 hertz or 60 hertz and within the power band, the voltage band. And that requires the system to maintain a balance between generation and load. So as you're adding new segments on after a fault, all these conditions have to be met. And then finally, maintain system projections after I add a segment on that had fallen off because the relay is opened and it's no longer powered. Now, what we're talking about is without people having to go and check that everything's okay, and then call on a hand radio to a control center that says, okay, I'm going to flip the switch back on over there, right? That's what happens in a major event, not just a normal operating event. Magically, this stuff will reconfigure itself and self-heal. Maybe not the entire configuration that was running beforehand, but more than you could do without this intervention, and trying to get to 100%. The whole goal, and we have a strong emphasis in the Department of Energy and the US energy community, is to provide more reliable, more robust, and threat agnostic power system resilience. Threats here are natural. It's a funny word. That's their word. It's not cyber threats. It's any kind of threat, whether a disruption due to malevolence, somebody trying to break the power system or whatever. So this automatic self-healing would be a great advantage. So I'll show you pictures of example systems in a minute, but just think of two relays on a line, meaning you have a long overhead power wire, usually at what I call low voltage. The transformers in Europe, it'll be on the ground, a pad mount, and it'll take that 4 to 12 kilovolts, and it will distribute it through a transformer to your homes. Typically in France, I know better than most in Germany, things 120 to 130 homes per transformer. Now I talk about that because that is a load to the higher system and it may have a relay on it. So those 120 homes may be activated by one device. So it's something to keep in mind. But there are many more devices all around the place, right? This particular project builds on earlier work, and just for those who might be interested, the things that it's improving are in previous ways of doing this without communications, when a segment went off, what we call an off-grid system, it had to be completely blacked out before you could find out where the faults were. This is electrical technical stuff. The isolation of faults needed to reclose into a fault. That means they had to connect the circuit for a second to find out what happened. Even though you know it's short-circuited, you have to reclose into it. You have to connect that again to see where the fault is. You're really flying blind, right? But you do this by, remember I said local nodes can only sense voltage, current, phase, frequency. So what you can do is find out how power is flowing around the place by taking those readings, and you can figure out where the fault was. It's really kludgy, right? And then finally, more automated transition into intentional island mode. When you want to isolate one part of the system, this will let you do it more elegantly. So those are advantages, but ultimately that requires that each relay device self-identify, somehow provide a tag that says I'm, and in fact what they measure is from a generator, from a source where the power is coming from, and the relay in front of that, you just count 1, 2, 3, 4 hops away from that power load. That's the only information they need to do this magic. Pretty simple. And again, I'm going in with setting very low expectations. We can talk about so many other things that we could measure and communicate using IETF tools, but for now, one tag, one value, an integer, 1, 2, 3, 4, 5. You could put more in the tag. They don't know yet how much we could give them, but that's what they want. Okay. So there are two approaches that they're thinking about doing this, and we're actually exploring. One of them is the Morse code approach. These relays, they're not supposed to do this often, but in these cases, you can tap them, you can open and close them, and the current going can be read by the next one down the line, and you have Morse code signaling. That's how these people think, okay? But it's gonna work because the wires, unless the wire is broken, and that's one of the things we can help with. Remember I said there are things that radios and IETF protocols can do that they can't. Well, this is one of them. And
so you have about 5 minutes left.
very good. So that's where we come and say, well, you really want what I'm calling secure next neighbor communications. So here we go. Basically, we can build on work that's already being done on the radio side with YSUN. I don't know how many of you know this, but I think because it's well known, and the relationship between 802.15.4 and IETF is so strong in many areas. So basically on the radio side, that's what I'm proposing, and I'll be here next week working with my friends in for a D and I think and next generation YSUN 5s and things like that. So that gives us equipment that we can use. It gives us some models, particularly for the channel models. It gives us modulation. It gives us plenty of bandwidth. Up to 600 kilobits per second is way more than we need. And of course, it gives us the ability to build on top of that with all of the nice 6-low stack and everything on top of it. I am looking at a couple of older RFCs, but to give you an example of how quickly our minds can go forward with requirements on understanding one of these segments versus actually doing something about it, and the resistance I talked about, the cultural commitments that don't match with ours, those date from 10 years ago, 2015, I think. Yeah, so we knew what we could be doing in industrial and urban sensing, but it takes some way to get your foot in the door. So some of the challenges are, like I said, we will have to figure out how to energize these things. And this is generally understood for equipment that's, you know, these microprocessors on distribution lines, but we'll dig into that and try to meet the cost requirements. The physical design so that these things can really talk to each other. I haven't yet got the mappings to actual locations and height, but then I'll talk about that, and then crafting the L3 through L7 IoT stack, and that's why I'm here. Right? So these are the models we use. You start with a small 13 bus one-line model, and you can test things out there. I mean, in simulation. These are packages of power system CAD models with extraordinary, MATLAB calculations and Simulink and everything all around them. So this is what my power friends do. The big one, the Iowa 240 bus distribution model, is very cool. And if you go to that URL, you can learn a lot about this domain, right? But the interesting thing there is we believe, to be determined, but we're quite sure that that one has physical location and height measurements. It's modeled on a real system. The other ones are not. So here, there's actually stuff out there, and I can measure the distance between these devices. And this is a power center. It could be a wind generator, for instance. And these are the relays on either side of it. They get opened and closed according to those principles or measures that I mentioned earlier. And so this is the domain in which we'll try to figure out how we can recover from a system event and attach more and more of these segments automatically using really nothing more than this metric of distance from one of those. So each relay will have a number associated with it. It will generate a number even after reconfiguration of how far I am from that nearest load. And that's what the algorithms need to self-heal. I'm almost done. So there's a lot of cool stuff here. We know that. I will be digging in. I am sure that the device integrity, identity, the firmware update, and this stuff is a whole, amazing toolbox that, by the way, my actual responsibility in this world, this workshop, is cybersecurity and communication. So I want all the good stuff, and they just trust me to bring it. But eventually there will be a scrub by people in the government who look at cybersecurity, and we will come out roses, right? So I'm very keen to get guidance and inspiration and collaborate on how to build the right stack for this application. And then it leads to something more exciting. There's sort of a holy grail, which broadens this from some of the narrow concerns that we're looking at to generalized fault location isolation and service restoration. There are centralized and localized versions of that, distributed versions. And I'll just say that the opportunity for machine learning and federated learning here is very strong. And so let's look at ways to use CBOR and very compact data to do that as well. I'll finish up quickly in getting the hook. I'd love to know who has used what tools to simulate these things. That's what I need to do to actually get to the next step with my customers. There's a table out there you can look at in the slides that sort of compares things. I'm not a strong simulation person, but I can get friends at work to do this. And then, yeah, thanks. That's what I have. I hope this has been interesting and a little bit thought-provoking, and I really hope to continue working with you all. Thanks.
Yes, thanks a lot, Craig. Very interesting. Fortunately, at the interest of time, we have to move on to the next presentation. But I guess you will have a write-up coming on this, in the form of draft or meetings, discussions where we can continue the discussion, or perhaps in an interim later on. But thanks a lot for sharing. Very interesting. Next up, we have Jaime. And yes, we have your slide coming.
All right. So hello, everybody. I think this is the first presentation of the week about AI agents. This IETF, if you have seen the side meetings, looks like an AI-related IETF. So today I'm going to be presenting our implementation of an AI agent that interacts with IoT devices natively. So I'm going to be presenting on behalf of the team. Let's get started from very, very high level with an analogy. So if you are a customer, you go to some professional, you give it a task, that'll be like an intent, something you want, and that professional will probably make a plan, will get a lot of tools, a lot of, like a hammer or a saw or materials, and following the plan will follow some steps, and it will give you back probably what you asked for. This is very analogous how LLM-based agents work. Some feedback. So the customer will be the user. The intent will be also natural language, what you tell the agent to do, and the agent will make a plan and follow the steps to try to accomplish what you ask for. So we built this basic system architecture for the agent. So it has, as I mentioned, it has a user. It's a bit further away. Further here. Here, good. All right. Anyways. All right. So feedback with the. All right. I didn't know that. So, all right. Maybe here. So yeah. So it has a knowledge base. It has. So the knowledge base would be the source of ground truth. In our experiment, is basically the web. So when the agent training data, the LLM data, is not enough, we will try to figure out more information, more ground truth sources to learn what to do. Then we have a physical system that we have plugged in. It is basically vanilla COA-based system, with standard protocols exposing standard APIs, and all the stuff that we know from IETF already. It has an LLM, of course, which is actually, the engine is not part of the LLM, but the LLM is like the thing that helps the whole agent to reason. And if you want to a very high level, simple definition of what the agent does, is actually a system that takes the user intent, decomposes into smaller actionable tasks, and then follows these steps, interacting with the system, getting feedback from the system until, for a number of steps, until the plan has been fulfilled and the user has received a response that satisfies the initial intent. Basically, that would be it. You can also run this, and I'll show it in the demo, in a closed loop automation. And yeah, so going a bit more into the specifics. So as I mentioned before, the knowledge base is a web search tool. I think it's a Brave API. You can have a headless browser. You can have other knowledge bases. So you can plug your CPI information of your product. You can plug some exotic, to paraphrase what the previous presenter said, like some exotic standard as well that is not part of the knowledge base of the LLM training data. Luckily, most LLMs actually have been trained already with tons of RFCs and drafts, so they know IETF specs pretty well. Yeah, and then as far as LLMs goes, we tried those so far. So GPT-4o, DeepSeek R1, Llama 3. For the planner, you probably want a more powerful LLM, but for a specific task, it could be that you could delegate it to a smaller one. Then the agent itself, we are using the small agents framework. So it's a React type of agent. So reasoning and acting is a common pattern based on something called chain of thought for building agents. This one in particular is a code agent. So every step of the execution, it generates a little Python snippet. It executes it and then it gets back the feedback. So it seems to be more reliable. There's publications about it. There's that claim that makes it more reliable than other mechanisms. Small agents also is model agnostic. So you can plug, as I had mentioned before, also the LLM that you like. We haven't tested, but it's also multimodal. So you could potentially use vision, audio, and other things. What we built were memory tools. So quickly you realize that the models these agents still hallucinate. They may invent functions, they may invent devices, they may try to contact things that don't exist. But you can build memory tools that help it anchor the information and be more reliable. So for example, we have a bookmarking mechanism, which is analogous to how browsers bookmarks work. So as you traverse co-op links and you find devices, you store them and the link attributes and any kind of relationships between those devices. We also have the execution history. So one of the problems is that the agents are non-deterministic, which you will see in the demo. of course, that is an issue. Although it works, the thing is that you don't really know a priori what's going to happen. It tends to work, but maybe in some cases you want to make it deterministic. So with this, you can store previous executions, and then if the user intent and the state of the system matches, you could reuse the previous execution. And then also user preferences, so you can learn over time. In our example is like a typical home automation example, but it's not. It doesn't have to be that. It could be something else. So it will learn about that. Now the physical system. So the devices we connect to is a simple Dockerized environment with few IoT devices. They are co-op based. They have the normal networking features, the normal link attributes, the normal, the normal co-op stuff, pretty vanilla thing, nothing too complicated there. We haven't done additions on the devices themselves. So the intention was to see what can the agent do with real life deployment, or it's not a real life deployment, but what a real life deployment probably looks like in many cases. Yeah, the serialization is JSON, sustainable JSON. You could have other serializations. Of course, if you use compression, you need to decompress it before you pass it to the agent, evidently. And then the interesting thing is the abstraction. So actually, with these 4 abstractions, you can do a lot. So out there, many of the systems, they tend to have a lot of tooling and giving a lot of options to the agent to select. It turns out that with these basic features, like how to discover things, how to get the current value of a thing, or modify a value of a thing, or subscribe and get notifications as the value changes, seem to be enough for the agent to operate quite efficiently. So the mappings, I mean, this is a standard co-op as well. So you have the discoveries done with a well-known core. You have the methods get, post, put, delete, and then you use the co-op observe option for receiving notifications. And those are basically the wrap around a function call, or in the AI jargon they call it tooling. So each of these function calls is a tool. So you have the list resources tool, the get resource tool, set resource, and observe resource. And yeah, so those are the primitives. And another demo, let's see. Here. Can I use this? Yes. So, let me just a moment. Yeah. Yeah. So the other day was a bit of latency. Let's see how it goes. So we have, let's just start. This is the first part is going to be the plain co-op stuff. I cannot make it any bigger, but I hope that people can see even in the back. So we just start the Dockerized environment with a few devices. This could also be an intro to co-op for those who are not familiar with co-op. So you start the devices, and then you have maybe a client here that you can ask things from the devices. So we have these functions. You can get for these devices, so you can get the air, the light, the purifier, temperature, and so on. So we can do a get, and we can receive the current values, the values. So the logic is simulated, the payloads are real, and the traffic is real. We can get the temperature. We could set values, so we can set the light to 0. That's basically switching off the light. As you can see, it's off. We can also, as we modify things, some of them are related to each other. So we could, for instance, set the thermostat to 18. And then on the temperature sensor, we would do observe and receive notifications until it reaches it. This one is for 10 seconds, but basically you will see how it changes periodically. So this is plain co-op stuff. Let's wait a bit until it finishes. All right, so now it's 18. Just a second. Yeah, so 18 roughly. And then we go to the agent part. So the agent, we start the agent. And then, so what happens here is that we tell it a high level thing. We can tell it a high level intent. Oh, something happened now. All right. Yeah, nothing to worry about. All right. So we ask it, for example, so ignore the printouts here. Let's focus on the question. So we have set up previously the light to 0, right? So we have switched off the light. So let's tell it, the agent, we can tell it like it is a bit dark, something very vague. Okay, I'll wait a bit. So we tell it this, and then it starts executing. And we will let the execution follow until the end this time and see what happens. Takes a few seconds. So that's another thing. Agents are definitely slower than real normal code. Not that this is not real. So what is going on? So we go back when we see the execution. Let me see if I'm not going to look at my screen because there's a bit of delay. So we tell it is dark, and then there is what the agent does. This goes into this React loop, and it has this fact checking. So it checks what is the user telling it that it is a bit dark. It's really hard to sync because the latency is pretty big. It is a bit dark. Then it has some facts, and it has some tooling. So as you can see here, it says list resources. So that's a real tool it can use. It plans what to do and what to learn from the system. And the current plan is that I will use the list resources to get the co-op resources. Then in the step 2, if there is a light, I will try to get the value of the light. And then in step 3, in this execution, is gonna maybe look into the web to see the better lighting conditions, and so on every step. For each, then it will go sequentially executing each step. So the first one is get the list of resources. And as you can see here, it will just execute list resources and print it out. So it does a well-known core on the multicast Dockerized environment. It gets the information. It's not totally fully compliant with the way it looks like in CoreLink, but we took some liberties to add, for instance, what kind of methods you can use, maybe a little bit of a description on the device of what it is. But that's pretty much it. And then it finds that there is a light resource. So then it goes into the step 2. So it will get the value of the resource, and it does that. And then it retrieves that the value is 0. And then it goes, it didn't do the web search in this case. And it's just based on the training data, apparently 400 lumen is good. So it will try to set the resource. And then it tries to do an observation, although this is not really necessary because it's instantaneous, but it will check that the value has been changed. And then it tells the user the value has been adjusted. So if I go back and I do the same thing, the value is 400. So the agent does not have any a priori knowledge of the device or basically anything. I can tell it more complicated things. Let's see what happens. So I could tell it it is also a bit cold. And remember, we set it up before to 19 degrees or 18 degrees. So it does also similar pattern. And what it should do in this, okay, so in this case, it's a bit different, the execution. All right. Just remember that this is non-deterministic, so I don't really know what it's going to do in detail. So it's kind of exciting to present to everybody. So yeah, so it's setting up an observation, and I will let it conclude, and then we go through what happened. If things work, let's see. So yeah, so it seems to work. So then we go back, and in this execution, it was very similar. Again, it looked for the devices that are available. Where am I? It is also a bit cold here. So it looks for the devices that are available, finds that there is a temperature resource, checks the value of the temperature, which is 18. I'll stop. There is the latency again. So it's 18. So, and in this case, it calls another tool called web search. So it checks on the internet what is the a reasonable good temperature for indoor environment. And you have some parameters here, 20 to 24, and so on. Again, if this was something specific of your systems and your products, it could check the CPI if you have some guidelines somewhere, and it would do the similar process, right? It could also even go into the websites. In the hackathon, actually, we were looking into that with this crawler development. So you could even locally enter the website, get the data, and try to see what to do. So, but in any case, the agent determines that 22 is a good temperature value, and it sets the resource thermostat to 22. So that we switch the thermostat, and then it starts getting an observation on the thermostat, on the temperature resource. So it's changed the thermostat and observes that the temperature of the room increases and changes. That takes a while because we simulate that too. But then for that, it uses co-op observe. And like, I mean, I find it very relevant to remember that it is checking the responses from the devices, and that goes back into the planner. So for instance, if it wouldn't find a device or information that could fix the user intent, it would change the plan and do something else. For instance, in the hackathon, we were testing actually it continues even more. So for some reason it checks again. It goes back into the planner, updates the plan, and it sees that it has changed to 22, and then it tells the user that it has changed. In the hackathon, we were testing with this, what was it, like a pancake machine, right? Like something odd. We could try that again. So what was it, like make a pancake, or make a pancake. So it will do a similar process, and most likely will tell you a recipe. During the hackathon, it was interesting that it also informs you, like, by the way, there is this temperature sensor and this thermostat and all that. So if we would have plugged a device that has the characteristics that could solve the user desire, it would have tried to fix it. It would have tried to do something about it. In this case, because it cannot do anything, it's just, for instance, it's trying to hallucinate things, and it's kind of like, let's see what happens. There is a maximum successful, good old fashioned, blah blah blah, surf hot. So in this case, it's just hallucinating. In the case of the demo in the hackathon, it tells you the recipe and then tell you about the devices that it found. But in this case, it's just hallucinating. So yeah. What else? Like you can run this in closed loop. So for example, once you have, so this is the user intent, what I just showed you. You could also run, let's modify it first. Yeah, well, it was 20 minutes, right? Yeah. So you still have time. Yeah. Right. Okay. So right. So let's just skip the closed loop automation then. But basically, you can run this, or let's do it very quickly. Like I can set this to 0, and then I can run the closed loop automation demo very quickly. And what it does, it takes the user intents and then it tries to fix it. If it observes every single device and receives notifications in real time, and it tries to fix it if it sees something that is out of bounds. So I just change the light again to 0, and then it will try to fix it for comfort. And yeah, so it will do that. Normally, it's very reliable. And here is where you can plug the deterministic approach. So if you have the same user intent and the same set of devices with a similar state, it will use just the deterministic one. So yeah, so that's basically it on the demo side. And let's go back to the slide quickly. Do I need to stop sharing? Thank you. How do I? All right. So what I show you in this demo, actually, there were no errors, but it's pretty good. So basically, what you tell the agent is you pass these tools that you have. You tell which model you're using. You pass the planning interval, which is how often do you want to go back to the planner to revisit the assumption. So you can put it very low if you are in a absolutely new environment. You want to rethink it every time. Also the maximum steps, so you don't want to run this forever. And you, after step 10, basically, it will just tell you whatever it has if it's not accomplished. Then the agent that I show you is not IoT specific. It is only IoT because I'm using CoAP as application layer protocol. You could use HTTP. The primitives in HTTP might be different. It might be that you need some tweaks. I mean, that would be interesting discussion in this IETF actually. As I mentioned, the knowledge in the agent, it doesn't have a priori knowledge. The knowledge comes from the user intent that the user is passing, the tool discovery at runtime, the metadata from the devices, if there is any, and the general knowledge of the LLM. The if it fails, it's pretty cool actually. It didn't happen in the demo, but if it fails, let's say that it passes. Well, let me go. I'll get into a moment. So you saw that it can interpret very vague intents, like it's called. If you make it very specific, like change the temperature by 1 degree, it will just do it almost 99% of the time. It still is a black box under the hood, so you cannot really know if it is that going to be the case. Right, like all the other stuff I have already mentioned. Yeah, so it can generate executable Python code, and if the code is wrong, it can pass the errors from the Python interpreter back to the planner to fix the Python code that was generated at runtime. So that is really really cool. It makes it more robust. We didn't get errors in this execution. Afterwards I can show you more demos. I'm sure we will get errors and we can try more. Then I already mentioned this, like the user is capable of finding the devices using well-known standards that we have been standardizing for decades now, like all the co-op properties, link attributes, resource types, meta types, all of that you can consume. Discover capabilities in real time, getting the state of the device in real time and incorporating that to the planner, and also observing the state until the task is completed. In the closed loop automation, the one difference is that you can pass a prompt with a specific configuration. So that is something different there. That is some a priori information, definitely. Yeah, then some learnings. So for those of you who remember, like this is a lot like a HTOS client, like a hypermedia driver of the application state client. They can operate effectively against unknown endpoints. So if you don't even have, so if we launch the agent and then you plug a new device and it's discoverable over co-op with, resource directory, multicast, whatever, it will still work in the same fashion. So what guides the agent is the hypermedia links and the things it finds during discovery. The planner can, I'm repeating again the same stuff. Same stuff, not tied to a specific deployment. So if you have a co-op ecosystem that is related to Lightning and another one that is related to something else, it should work providing that you have the right semantic abstractions as well. And then so the agents are not task specific, they are proactive. They try to solve things in real time. I already mentioned about the minimal subset. I already mentioned as well, IETF specs are already part of most LLMs, so they are very aware of the specification. They understand what is a co-op message. They understand what is REST and that type of abstractions. The standardized affordances can help the agent functionality. Maybe there is some work that could be done also in that respect, actually, standardization-wise. And actually, it turns out that the co-op device-to-device design is really well suited for agents because you have discovery, you have observe, you have subscription, REST pattern, smaller payloads, which help the agent make better decisions. You have a large 2,000 lines of HTML, it can get confused. And this simple abstraction of these 4 functions actually works really well. And then, I already mentioned that it's non-deterministic, that you can make it more deterministic. The recovery I didn't mention, so it is quite robust. So it can recover from execution errors. So you can, as I mentioned, you feed the Python interpreter back. It can recover from interaction errors. So you get a 4xx, goes back to the planner, and the planner will try something else to try to accomplish the thing. And then even outcome errors. So it will keep trying until the user intent is fulfilled, or it will just tell the user something that it didn't manage, or that a hallucinator just end at the end of the planning stages. And then that's it, like the last slide. So these are fundamentally, the main thing to know about this is that it's fundamentally different than normal software development cycles, because normal software development, you build your code, you compile it, maybe you flash it on some device or you run it somewhere, and it's specific and tailor-made for a specific purpose. And if you want to change something, you have a new feature and you have to do it again. In this case, agentic systems, they adapt to new feature requests. They can come in the form of new intents, new devices, state changes in the devices, a new knowledge base, and they do it at runtime. And that is a really powerful concept. I mean, I believe there will be more of this in the future. And and thank you for the time. That's it. Sorry if I take too long. No, it was roughly 20 minutes.
Yeah. No, thanks a lot, Jaime. I think it's super interesting. And I guess it shares we're a bit optimistic in our scheduling. Because we have well, very interesting topics that worth a lot of discussion.
There is
Maybe we
one,
can have one really quick comment before we.
I'll be here afterwards, and
Yeah,
you know
and
we can
we can
discuss more
definitely
if you're
continue
interested.
this in an interim meeting.
Yes, hello, Alexander here. So thank you very much, and I find it super interesting. Of course, tons of questions. The first question, and like a first observation, is I think that it's really interesting to see what has been done with within the IETF and T2TRG that makes this possible, right? Like SNML and co-op and all this, right? Because
Right.
without that, you cannot really, I mean, you have like the 22, but what is 22? Is it Celsius? Is it something else?
Yeah,
So
the semantics.
how exactly? And just a super short question, like how do you have okay, there are two questions. Okay, let's pick the easiest one. Like I say, okay, I'm cold, so it starts saying, okay, 22, but then it takes some time for the temperature to reach that room temperature, right? So maybe how does it? Did you try? How does it work with maybe several sensors when it's going
Yeah,
to
I
have
mean, like
one?
we have five
two-
sensors in this case. We have more sensors, and you would need more semantics to distinguish which one are you talking about, to tell the agent which one you're talking about. That could be worked out. But I mean, it's just a sample environment. It would be nice to test on more real-life environments to see how what semantics the devices are sending and how they interact. But if the core primitives are there, it should work the same. And also, I didn't mention it, but like this is natively talking IETF core protocols without intermediary frameworks. So you don't need like an intermediary like MCP server or another entity in between to do the same thing. So that's also another bonus, I think.
Thanks.
Very good. Thanks a lot. And apologies, Marco, that you have only 14 minutes.
Hi everyone, this is Marco. Thanks for this lot. This is a brand new draft submitted just for the cutoff of this meeting, but the idea has actually been in the open for a few years and got quite some good feedback, especially during hackathon discussions from a number of people. But now we have a document. So the motivation for this, of course, it's very important during the life cycle of the device to regularly update it as updates of different natures come up for the sake of fixing security vulnerabilities, adding functionalities, update set of root of trust, whatever. And of course, you want that process to be secure and reliable, but also efficient in terms of performance, and it's supposed to scale well depending on the number of devices you want to update. There's also, of course, a lot of work happened in the SUT working group in terms of architecture, the manifest information model. The serialization in CBOR is almost out there as an RFC. So that's a very good body of work to use, definitely. In parallel, in the co-working group, more abstracting from the use case, there's been a lot of work on communication and group communication also with security. So at some point, the research question came up. Can we use those core building blocks to find a way to distribute efficiently and securely software updates to a fleet of devices as efficient as possible? Of course, protecting the actual distribution of the updates in question. So with this motivation, the contribution now compiled in this document is about a method for a group distribution to a fleet of device in a secure way of software updates of whatever nature, can in practice be a firmware, with protection end-to-end. We'll see better in the next slides, covering first a high-level architecture, then the practical processes of advertising the availability of an update in the first place, and then distributing the actual update. As mentioned, it uses a number of building blocks for core, but mostly, well, the co-op protocol, the blockwise transfer for co-op, and end-to-end security with Grupos core, which is the variant of OS core, to protect the communication end-to-end. And an early idea of this, the first consolidated variant was presented actually 1 year ago in Paris at the on-site T2TRG interim meeting, and well, you can find the slides at the link in this slide. On the building blocks, there's a whole section in the document going through them one by one and giving a very short summary, but these are the most important ones covered. Again, the co-op protocol, for which a number of notable extensions have been standardized in the past years, mostly observe, for literally observing the change in the representation of a resource at the server and automatically get back notifications that you are subscribed to those. The blockwise transfer, so fragmentation of large data body at the co-op layer to be sent separately at different co-op messages. In those messages, payload. and the possibility to use co-op and possibly even blockwise for co-op, not only on UDP as originally intended, but also the reliable transports like TCP, in which case you can have security, for example, with TLS. But then there's also been a recent body of work on co-op group communication that detail the use of co-op mostly over UDP and IP multicast, but in general for group communication, considering a variant of the OSCORE security protocol for achieving the same security guarantees in the group communication environment, and adding some extra fancy stuff further building on those for the sake of caching, end-to-end protected responses at proxies, even though they are protected end-to-end, but effectively being able again to produce a cache hit and serve a protected response from a cache, and also one-to-many responses, especially if observe is used. With this in mind, this is really the high-level, most high-level possible overview of this approach, assuming for a while that the knowledge of the availability of the update has already been spread around, and it's about fetching the actual update. The distribution is based on a pool model. So a distributor server is somehow queried to provide the update to an intermediary proxy that caches that update and then takes care of distributing that update to all the devices in the fleet with as least messages as possible, meaning multicast one-to-many messages as responses. The additional nice thing here is that the distributor itself provides the software update to the proxy in large blocks. Think of large chunks or inner chunks using blockwise for co-op at the co-op layer. But then in turn, the proxy further fragments those chunks into smaller outer chunks that are practically sent with one-to-many messages to the devices. And again, the proxy takes advantage of caching. This is the gist, and then the detailed process builds on this mind model. As to the design goals, well, here they are. We want, first of all, end-to-end security between the distributor server from which the updates is, first of all, pulled from, and the final consumers, so the devices in the group, and that can be achieved with the group OSCORE security protocol. And in terms of access control, you can be very fine-grained if you want. There are even solutions for that. To keep it simple, you may just want to set up one security group for this, and you have the guarantees that if you somehow authorize someone to be in the group, well, it's authorized to get this update, essentially. Taking the legs separately instead, considering the distributor side, we want to limit the interaction with the distributor as much as possible to annoy the distributor as least as possible. Well, that builds on the deployment on the proxy, on the cacheability that is possible for the proxy to do on the messages retrieved from the proxy, and on using blockwise for co-op between the proxy and the distributor using large chunks, which is something enabled with blockwise for co-op over reliable transport. If we move instead on the leg between the devices and the proxy, we want also to limit the interaction with the devices as much as possible and avoid lockstep transfer. And that is also possible to achieve, well, largely relying on the proxy and using one-to-many messages to transfer the data to the devices. But of course, these are constrained devices on constrained links at that segment of the system. So if you really want to take care of that aspect, it's really about the second fragmentation operated by the proxy that practically distributes small outer chunks. Okay, on the architecture, this figure is literally taken from the document. It took a while to draw in ASVG, but I think it was worth it. These are the four actors. The author is, in principle, a human being preparing the update to distribute as a binary image, but also a manifest associated with that, specifying a number of metadata, and typically the size of the image, a signature on the image or the hash of the image made by the author himself, and other metadata related to the software update. Those are loaded on the distributor by the author, and the distributor is the server that is hosting an appropriate number and type of resources where the manifest and the image are stored and are taken from. Then we have the proxy, as I mentioned before, deployed between the devices to update, and the distributor hosting the image and the manifest. And the proxy is practically going to take care of pulling the data from the distributor, caching as much as possible, and distribute to the devices on the legs called B and C. And C in particular builds on one-to-many multicast responses that practically transfer chunks, small outer chunks of the software update to the devices. So how does the process practically work? First of all, it's about notifying about the availability of the software update. And this is pretty simple and was clear from the start. It was even in the previous presentation in Paris. Under the architecture still considered, it can really be based on co-op observe, where essentially the devices observe the manifest resource at the distributor, and well, they're going to be automatically notified by means of a notification transporting the manifest, just to say this new version of this software component is available as an update. But still, we have the proxy in between caching this response like any others. So, okay, for the first ever device coming and asking for, is there any update here? Yes, the proxy will reach out to the distributor and pull the manifest from the distributor, but then that will be cached. And following clients, or the same one for what is worth if it tries again, can just retrieve the same manifest from the proxy cache. So again, limiting interaction with the distributor as much as possible, and overall the time to serve a device here. So this is the way they learn about an available software update. The process for actually distributing the software update, at least the way I tend to imagine it, is to be divided into epochs. Where each epoch is about distributed one of the large inner chunk, essentially. When it's over, it just resumes, and it continues in a loop as devices come to request an update. It's just an infinite loop in principle, and devices can try to intrude in at any point. Basically, this is properly handled by the proxy, and eventually the device will be able to have gotten all the large inner chunks to compose the whole image, to cross-check the total amount of bytes received against what the manifest said, to verify the integrity, and so on. But think of epochs, each to transfer one large inner chunk, as we said, further split. In turn, you can imagine the epoch split into subphases. I'm going to go through them one by one, but at a high level, at the beginning of the epoch, we have an admission phase where a device can really say, I'm interested in getting the large inner chunk for this epoch, count me in, and then the transfer will actually happen in the full transfer phase right after for that inner chunk. But then we're given the possibility in the immediately follow-up recovery claim phase for the devices that have just obtained or were just interested in participating in this epoch to recover any small outer chunks that may have missed here, and they're going to be transferred in the recovery transfer phase right after. There's an epilogue on the proxy to clean things up and get ready for the next epoch, and in fact, at the next epoch start right after. So checking that with a bit of a zoom in, the real kickoff for the proxy here is receiving a first request, a header. Well, before that, no transfer of this software update has really happened. And that, of course, will mean for proxy to reach out to the distributor, obtain the first large inner chunk for that software update and get ready. We are into the admission phase there. Well, for a certain amount of time between the beginning of the epoch and TA determined by the proxy is welcoming requests from the devices that are enrolling for receiving the inner chunk for this epoch. The proxy guides this process and the devices specifying in reply to their request an error response containing some information from what is going to happen. So it's going to instruct the device with that error response about transfer specific information for receiving the responses that are going to come. It's giving a timing indication about when they're going to come, so not before the time TA specified and decided by the proxy. It's also going to give the inner index for the current epoch, so the index of the large inner chunk is going to be transferred in the epoch to give an idea of where we are in transferring the software update. Just remember that this is a loop in principle, and the device can join at any time, so you need to tell where we are thinking of the big picture and the whole update. But then eventually the time TA comes, we are in full transfer and the proxy stops accepting requests for enrollment here. If they come, it replies with a different sort of error, essentially saying, come back later at the end of this epoch. You are too late for participating in this round. But other than that, the point of the proxy in the full transfer phase is to send back-to-back a number of one-to-many responses over multicast, each of which transfers one small outer chunk of the inner chunk of the current epoch until all are transferred.
Marco, we're starting to go over time.
Ouch.
Sorry.
Yeah, so I think since we are not making any crucial decisions at this point in time, we can just continue on for 5 more minutes as a hallway meeting. Use the room as a hallway.
Thanks, Harry. Recovery claim, it's an opportunity for the devices that were enrolled and participated in the previous admission and full transfer to recover some outer chunks that they got lost. So they can ask for a retransmission in their interest during the recovery claim. And the proxy is basically going to collect those requests and replying with error responses instructing on how to participate in the recovery transfer that follows right after a time TB. When that time comes, the recovery transfer starts, and it's about sending one-to-many responses, but only for the outer chunks that were claimed to be lost and have to be sent. Eventually, even that finishes. I'm skipping a lot of details here. We are into the epilogue is just cleanup for the proxy, updating inner index accordingly to get ready for the next epoch to start, and the process repeats. This is the actual transfer. If you look into some more security-related things, of course, it's about checking that the update has been fully received and intact as intended. You have different ways and different points in time to check this. Of course, at the very end, it's really about checking the signature that was present in the manifest from the author. Of course, that has to be done. That can happen. It's a good check already. This is also introducing some possible intermediary checks. The devices have the possibility to check the integrity of each big inner chunk when all the outer chunks about it have been received at the end of an epoch. And that can be done by verifying the signature in a grouposcope protected response. But then there's yet another layer. What about the small outer chunks in each epoch? If they were not protected at all in terms of integrity, and if we don't do anything special, they are not, well, it's not the end of the world. Things will fail later on anyway, but that can really become an easy denial service vector to exploit for an adversary that can just tamper with something and the devices won't notice until all the inner chunk transfer has been completed. Well, it's just a pity. So that needs to be fixed also, because this attack can become even very efficient for the adversary by taking advantage in their interest of the multicast message delivery. So to fix that, we think about adding a short checksum in each of the outer chunks, practically added as value of a new co-op option that the proxy adds in each response transporting an outer chunk. The MAC is practically computed by the proxy before sending that response and added to the response, and then it's of course recomputed and checked by the devices receiving the response. To cut it short, computing that MAC requires a key that is trivial for the devices to compute from the group material, but in principle, the proxy is not a member of the group, so it cannot trivially compute a key. So how can the proxy get the key? It needs to compute the checksums. It's about distributor providing that key in advance to the proxy when providing the proxy with the inner chunk to distribute for that epoch. And there are two different ways in turn for the distributor to provide the proxy with that checksum key. If the proxy and the distributor already share a secure communication channel, for example, they're using TLS on their leg, well, then it's just fine to give the proxy the key in the payload. That message prepended to the original payload. And that's actually the preferred way if those two nodes are sharing already a secure channel. In case they are not, well, the key cannot just be put there and possibly visible to some external observer. It can still work to prepend the original payload with additional data intended for the proxy, but that in turn has to be separately protected by a security wrapper, for example, using HPKE in COSI. I think that'll work quite well. Well, there's some proposed encoding to make that practically happen, having this particular use case in mind, but I believe it can be generalized to the point to be maybe considered even in the core working group as a feature for core, but for further discussion. That's it. Most of what I intended is in the draft already. Actually, in terms of design and protocol, I'd very much like to add a concrete example of message exchanges, showing this in action, and to detail a little bit on the provisioning of the map key from the distributor to the proxy in the case where they use, for example, HPK for COSI, and the distributor would be required then to know in advance the public key of the proxy to do the HPK wrapping, and that non-trivial security considerations. And Carsten also recommended to do a nice exercise, at least a functional comparison with other approaches for lost blocks and recovery approaches to recover missed blocks, mentioning Flute and Norm. I'll have a look into those. But that's what I have for now, and thanks a lot.
Great, thank you, Marco. And and apologies again for everyone for a bit tight schedule, but thanks for very interesting discussions, and we'll continue on the mailing list and on future interim meetings, clearly around security topics, bit of AI, interoperability. We're gonna need to have future work to be done. So looking forward to seeing you all at the interim meetings at the mailing list. Thank you and see you soon.